Hello, everyone. Welcome back to Codex. Today's speaker is Ben Adcock from Simon Fraser University. Professor Adcock is an expert on approximation theory, scientific computing, and the mathematics of machine learning. Today, he'll tell us about deep learning for inverse problems, confident hallucinations, and new theoretical guarantees for Bayesian recovery. Take it away, Ben.
Great. Thanks very much. So first of all, let me start by thanking Mike and Emily and Co for the invitation. It's really nice to have this opportunity to talk to you all today. So as Mike said, I'm going to talk about deep learning for inverse problems. This is part of work that I've been doing for quite a long time. And this is joint work with a bunch of people, including Vegard Anton, who's now in industry, Juan Cardenas, who's just started a faculty position in Chile, Nick Dexter, who's assistant professor at Florida State, Nina Gottschling, who's at DLR, the German aerospace company, Anders Hansen, my longtime collaborator from Cambridge, and my former master's, now PhD student, Nick Huang. Okay, so let's get started. This talk is about image reconstruction. So what are we going to be looking at? So we're looking at recovering an image from measurements. This is a fundamental task in many, many applications in science and engineering and industry. So typical examples arise in medical imaging, MRI, CT, ultrasound, PET, SPECT, et cetera. Then, of course, you have scientific imaging, so electron microscopy, radio interferometry, fluorescence microscopy, et cetera. And finally, of course, you have very many different types of industrial imaging, so seismic imaging, infrared, light field imaging, lenses, et cetera. So just to visualize, here's the task. We get some measurement data. So this is CT measurement data for anyone who knows. This is the famous sinogram that you get in CT. And your goal is to go from this data and recover whatever the image is. Okay, so in this case, it's a knee joint. So this talk is not about the sort of mathematical modeling of imaging problems. So I'm going to skip over all of that and say that in many problems in imaging, you can think of a very simple, discrete mathematical model for your problem. So I'm not exactly sure where we cut out. So I just described this is our mathematical model. So we want to recover x from its measurements, y equals ax plus e. So what makes this challenging? What's the key challenge we'll think about today? In practice, the number of measurements, m, is much smaller than the size of the image n. Okay, so this arises for various reasons. So, for instance, in MRI, it's related to the scan time. In CT, it's related to the radiation dose. Seismology, cost. Other applications, it might be power or various other constraints. Okay, but in many sort of imaging applications, one of the primary goals is to either reduce the number of measurements or get sort of high quality images from a fixed number of measurements. Okay, so if I was giving this talk 10 years ago, I would be talking about model-based imaging methods. So starting around 2005 with the advent of things like compressed sensing, there was essentially let's call it a revolution in imaging, in inverse problems in imaging, which is what I'll call the model-based imaging revolution. So what is the idea? The idea is that one tries to model images using certain handcrafted low complexity structures. So for this, I think of something like gradient sparsity. So think of images as objects whose gradients are mainly zero. Or you could think of wavelet sparsity or something like that. And there are many variations. There's a huge sort of line of literature on sort of sparse modeling of images. Then once you have your handcrafted model, the idea is you try and recover from the measurements. So you try and fit the data whilst promoting that handcrafted structure. So a typical example would be something like TV minimization. So you solve this convex optimization problem here, where on the one hand, you fit your data, and on the other hand, you try and minimize the TV norm, which is promoting gradient sparsity. Yeah. And so this is all very nice. There's a huge literature on this. And one of the nice things about this is you get recovery guarantees, you get guarantees on accuracy and stability of your recovered image using the theory of compressed sensing. Okay. So this revolution had a substantial impact. So, for instance, there are commercial MR scanners that use these techniques, and these techniques are used in many other applications. I'd also say, from the sort of more general viewpoint, the impact of this has been to sort of fundamentally change how we now think of the task of image recovery. You know, we now think of images as having low dimensional or low complexity structures that should be exploited in some way in the recovery process. Okay, so what happened in sort of about 2017? Arguably, people started increasingly to use, rather than handcrafted models, to use deep neural networks instead. Okay, so the idea is to take advantage of some training data and train a deep neural network. And so in some way, what you're doing here is you're implicitly learning an image model, okay, rather than handcrafting an image model, like with, say, gradient sparsity. So why might this be a good idea? I don't think this needs too much motivation. Deep learning is the state-of-the-art tool for image classification, has been for over a decade. And now, of course, it's state-of-the-art for things like image and video generation as well. So what can you infer from this? You can infer that deep neural networks are very good at capturing important image content. Okay. So this has sort of led to let's say, the second revolution in inverse problems in imaging, which is data-driven methods. So in the last 10 years, there's been a huge explosion of deep learning techniques for image reconstruction. There's a zoo of different techniques out there, far too many to talk about in this talk. But I've listed a few here. So there are and some of these we'll see later in the talk. There are things like fully trained models, unrolled optimization solvers, learned regularizers, deep equilibrium models, deep image priors, generative model priors, and posterior sampling with generative models, which is something I'll return to at the end of the talk. And these come in all sorts of flavors, typical machine learning flavors, so supervised, semi-supervised, unsupervised, et cetera, et cetera. What's the general idea? The general idea is you take some training data. So that training data could be ground truth images, it could be measurements, it could be both, depending on the setting that you're thinking about, and use that training data to learn a reconstruction map. And this reconstruction map typically is a deep neural network or involves a deep neural network in some way. So what is this? This is a map psi that takes you from your measurements y and produces your image x. So it's been nearly 10 years since people have started doing this, and there's been a lot of progress. I see there's a question in the chat. Oh, that's just from Emily. Yeah. And so it's now sort of well known that sort of state-of-the-art deep learning methods for inverse problems can significantly outperform more standard model-based methods in terms of reconstruction accuracy. However, one of the key issues that we're going to dwell on quite a bit in the talk is that these methods have been observed to be prone to hallucinations. So what do I mean? Deep learning-based methods for image recovery can produce realistic-looking but ultimately false artifacts in the image. And we'll see some examples in a second. And so I want to stress that this is a serious concern, okay, especially for any kind of safety critical task, such as, for instance, those that arise in healthcare. Okay, you don't want your image reconstruction algorithm to produce any kind of hallucinations for these settings. So let's dive into hallucinations a little bit more. So I want to just show a couple of examples of the kind of effects that have been observed. So here's an example. This is a parallel MRI example. This example comes from the Facebook Fast MRI Challenge, which is one of these sort of open competitions for using machine learning techniques for MRI. So here's the original image. This is a brain image. This is a crop of the image. And this is the reconstruction that you get via deep learning. And you can see that it's hallucinating features here where the red arrows are. Here's another example from the same challenge. Here's the image. This is the original image, and you notice that the deep neural network has hallucinated this artifact in the brain here. Okay. You also see this in various other imaging applications. So this is an example from optical microscopy. So again, the deep neural network reconstruction is hallucinating these artifacts here. And here's another example from fluorescence microscopy. So again, you're seeing features being hallucinated in the recovered image. So this phenomenon of hallucinations is now very widely reported. So I pulled out a few quotes here. This is a quote from the report on the Fast MRI Challenge from 2020. This is a paper about fluorescence imaging. This is a paper about microscopy more generally. And more recently, this is an article that was in Science News by Martin Berger and Tim Roth. And one of the things they end with is by saying that data-driven methods exhibit enormous potential, but will only be of use if they can prove their resilience and lack of hallucinations. So there's a lot of empirical evidence for hallucinations. But one of the things that's not really been addressed or hadn't been really addressed was why do hallucinations occur in in-birth problems? So we started to think about this a number of years ago, and what this eventually led to was a publication that appeared in Science Review last year. And what we aimed to do in this paper was to establish sort of theoretical mechanisms that imply the presence of hallucinations in an image recovery task. So I'm going to illustrate with this with a couple of the main results from the paper. So here's the first one, and this is what we call detail transfer. So suppose I have an image X, and I have a detail X det, and this detail lies close to the null space of my measurement matrix A. Now, suppose I have a reconstruction map, and suppose it's Lipschitz, a very mild assumption, and suppose it recovers the detail image well. Okay, so by the detail image, I mean X prime, which is X plus X det. By recovering it well, I mean that if I take the measurements of X prime, I recover them with psi, I get something that's within delta of X prime. So then what happens? Well, now suppose I take psi and I use it to try and recover the detail-free image. So that would be the image X. So I apply psi to AX. I can add noise if I like. And now what happens is my recovery of psi is now suddenly close to X prime. Okay? So in other words, the detail that was present in X prime has been transferred by psi when recovering the detail-free image X. So let's unpack this a little bit more. We have a detail that has small measurements. Okay, this can occur very easily because keep in mind that our number of measurements is less than our ambient dimension, so our matrix has a huge null space. So there are lots and lots of possible details that live close to our null space. Our map psi, you can think of it as overperforming in the sense that it recovers the detail image accurately. And the consequence is that it transfers this detail when recovering the detail-free image. Okay, so it underperforms on X, and in particular, it transfers the detail. So you could also think of this as a statement in terms of false positives. So think of X det as a tumor, for instance. Think of X as a healthy brain. Think of X prime as a brain with a tumor. So then your reconstruction map psi is going to recover the healthy brain and hallucinate a tumor, so a false positive. So a couple of key points. So first thing to say is these are extremely weak conditions. Okay, all we're imposing on our reconstruction map is that it's Lipschitz and that it recovers the detail image well. for some detail that's close to the null space. And the other thing I want to stress is that if you are doing some kind of learning, so you're designing your reconstruction map by minimizing some kind of loss over your training data, it might be very easy to train a reconstruction map that recovers this detail image well. Okay, in particular, if it lies in the training set and you're able to drive your training error down to zero. The
Sorry, Ben,
second key point,
could you go back to the formal statement?
yes.
So, so the thing that'll cause the hallucination is this condition that when you apply the map just to the detail by itself, that it's small.
Yeah.
Does it matter what norm it's small with respect to?
Uh, so this norm can be any norm. Um, uh, yeah, so I think yeah, so these can be arbitrary norms, I think. And then your Lipschitz continuity will be with respect to those norms.
Okay,
Yeah.
thanks.
Um, yeah, so and the other point is there's no your map psi does not need to be unstable. Okay, we'll talk about instability next, but for this result, your map psi can be completely stable, and this is important. People, there's a line of work that tries to ensure that when you train a map that is stable, that has small Lipschitz constant, for instance. Okay, let me illustrate an example. So this is an example from the paper. We wanted to get the paper in Cyan Review, so we showed an example using the Cyan logo. So this is a highly synthetic example, but just to illustrate the point. So here's my healthy body part, X. Here's X plus X det. We've set up X det so it's close to the null space. Here's the reconstruction of the detail image. So X plus X det. It's recovered very well. Now here's the reconstruction of X, and you see we've hallucinated the detail. So this really does occur in numerical experiments. Okay, so that's the first result. I'm going to show one other result from the paper as well. And this is the phenomenon that we call over or inconsistent performance. So now suppose we have two images, X and X prime. We have a reconstruction map that's continuous. And suppose that X and X prime have similar measurements. Okay? So their difference lies close to the null space. Psi recovers X well. Okay? And then for X prime, psi recovers X prime close to some other image, X double prime. We'll talk about this more in a second, where X double prime is far from X. Okay. So this is a little bit, maybe a little bit unclear for the moment, but we'll talk about it more in a second. Then your map psi is unstable. So precisely its Lipschitz constant behaves like X minus X double prime divided by eta minus 2, where eta is essentially the accuracy that you're getting here. So that's the instability statement. Moreover, it hallucinates. So again, you can you try to recover an image that's close to X, and you get something that's close to X double prime. Okay, so let me explain a little bit more what's going on here with some pictures. So here's the picture for in the case of overperformance. So let's suppose X double prime is equal to X prime. Okay, so the theorem conditions in this case says that psi is recovering X and X primed well. So you have this kind of picture. Think of X and X prime as far apart. Their measurements are close, and then your map psi is able to recover them accurately. Okay, so your map psi is sending measurements that are close to images that are far apart. Then it should not come as a big surprise that something is going to go wrong. And what's going to go wrong is that the map psi is unstable and it also hallucinates. So that's the overperformance picture. The inconsistent performance picture is something like this. So suppose you have two images, X and X prime, that are close. Then Generally speaking, their measurements will also be close unless you have some very weird A. Um, and now you're saying that your map psi sends them to things that are far apart. So you can think of this as sort of inconsistent performance. Say if it's recovering X very well, but it's recovering X prime very poorly because it's sending the reconstruction of X prime to something that's far away from it. Yep. Then again, you run into the same issues of instabilities and hallucinations. So the key point, um, your map psi should not be able to distinguish X and X prime because their measurements are close to each other. Yeah. But the consequence of it distinguishing X and X prime is that it's an unstable and a hallucination. Yeah. So it's really trying to do something that it shouldn't be able to do, and therefore necessarily it becomes unstable and hallucinates. Now, the key point here is that this situation can easily arise when you're training a reconstruction map from data. Okay, so if X and X prime belong to the training set, you drive your training error down to zero, then your map is going to be able to recover both of them well, and therefore, if their measurements are close, it's going to become unstable. Yeah. And so again, it's hard to prevent this from occurring. And in particular, what makes this hard is that these are extremely weak conditions. All you're saying is that you overperform on just two images, X and X prime. Yeah. The other thing to point out here is that these are not rare events. So you could perhaps try and say, well, maybe these are just rare events. Maybe they occur in some sort of set of measure zero or something like that. In fact, if you go back to the statement, you'll notice here that everything is formulated in terms of the existence of bulls centered at certain points. So these are not rare events. They're not sets of measure zero. You can also set things up in a probabilistic sense and quantify the probability of them occurring. Okay, so then just one remark I'll mention, but I won't discuss in any detail here, is that if you look at model-based methods, they are really not susceptible to these effects in the same way. Model-based methods essentially cannot overperform in this type of way, and this is something we discuss in more detail in the paper. Okay, so here are a couple of examples. So here's deep learning method for MRI. Here's an illustration here. So this is the image. Add a little bit of noise, and what you see is this hallucination here. Here's an example of instability. So again, you add a small amount of noise and you get significant artifacts, again, indicating instability in your reconstruction. Okay, so to summarize, for the reasons that we've discussed, many machine learning-based methods for robust problems are susceptible to hallucinations. In general, you can argue that hallucinations arise when a learned reconstruction map overperforms in some sense, and it overperforms in the sense that it recovers objects that are close to the null space of your measurement matrix. So there are quite a few further results in the paper that I'm not going to discuss. You can talk about in-distribution hallucinations. You can show that they occur with high probability, subject to certain conditions. I also mentioned that these are not rare events. That's elaborated more in the paper as well. And then finally, another thing that we show in the paper is that good generalization may be impossible in certain cases, regardless of your training set. Okay, so actually, in some sense, the learning problem you're trying to solve actually doesn't have a solution. Okay, so moving on, I want to talk a little bit, just to end this discussion about hallucinations, I want to talk a little bit about some work in progress with my PhD student, Nick Huang. So up to this point, we've been talking about reconstruction maps So these are maps from your measurements, and they give you an image. Okay. So this is often called a point estimator. Okay. You take your measurements, and you get a single image as the recovery. But people are very interested in imaging, and also many inverse problems in general, of not just recovering an image, but providing some kind of estimate of confidence. Okay. And in particular, if you know that there's a potential for hallucinations, you might hope to use your confidence estimates to potentially detect hallucinations as well. So there are various different ways in which you can do this. One line of work looks at essentially set-valued reconstruction maps. Okay, so the idea is now these provide confidence intervals. So your map now takes you from measurements, and rather than an image, it provides you uh, a, a little box around a single image, and these are intervals that give you estimates of confidence. So you can do this with what's called interval neural networks, for instance. So that's one approach. Another approach is to do a Bayesian method. Okay, so essentially try and learn the posterior distribution of your image given your measurements. Yeah. Okay, so there are many other techniques for estimating confidence as well, which I won't go into. But what I want to illustrate is that in either of these settings, you are still will be susceptible to the same kind of mechanisms that we showed previously can cause hallucinations. So let me illustrate this fairly briefly with a couple of example theorems. So suppose I consider set-valued reconstruction maps. So these are maps from your measurements to the set of bounded subsets of CN. Yeah. Then you can prove a very similar looking theorem. So suppose you have a detail that's close to your null space. Suppose that your reconstruction map is Lipschitz, and suppose that it confidently recovers the detail image. Okay, so in other words, the Hausdorff distance between the set containing the detail image and your reconstruction from its measurements is small, less than delta. Then psi is going to confidently hallucinate when recovering x. So in other words, the Hausdorff distance between x primes and the recovery of x is going to be small as well. So this is saying that not only are you recovering something that's close to x prime, but you have high confidence of it as well, because your set is close to this singleton. You can prove a similar result if you look at probability measure value maps. Okay, so now suppose that psi is a map that takes you from your measurements and gives you a probability distribution. Okay, so this could be the posterior. So again, the same setup. Now suppose that your detail image is recovered well in a suitable sense. Then again, you confidently hallucinate your detail image. Okay, so for I'm going to omit the details, but you can also generalize the results that I presented previously about over and inconsistent performance as well. So again, the conclusion is much the same. Over or inconsistent performance implies instabilities and confident hallucinations as well. So okay, so to summarize this part of the talk, what we've seen is that learning-based methods can confidently hallucinate. Uh, uh, and in particular, we've seen that these effects are not just limited to methods that provide point estimates, they also occur for methods that try and provide confidence estimates as well. So the question is, what can we do about this? So I think it's worth to just dwell a little bit on some of the sort of recent history. Around sort of 5 to 7 years ago, I think there was great optimism that one could simply take a bunch of training data. So, for instance, ground truth images and their measurements, and then just throw this formulate this as a training problem and learn a deep neural network to perform the reconstruction. And that if you had enough training data, this would all work well. Okay. And you did your training sufficiently well, you set up a suitable architecture, et cetera, et cetera. And this was popularized quite substantially by the development of what are called sort of fully trained or learn the physics models. And so that's doing exactly what I said here. Yeah. One of the advantages of this, if you could do it, is that you now actually don't need any knowledge of A. Okay, so you're really you A is encoding the physics of your measurement device. So if you're just training from this data here, you don't need to know anything about the physics, which is nice because your modeling of your physics is never exact. You can just learn it from the data and get good reconstruction. Okay. However, it's now been sort of 5 to 7 years, and I think arguably it's fair to say that these approaches utterly failed. Um, they were there were issues. Well, first there were computational issues, but there are more pressing issues such as hallucinations, instability, and also inconsistent generalization. So here's just an illustration to make this point. This is using this automap approach. Here's an image. We add small amounts of noise to the image, and then we try and recover each of these. If your reconstruction map was nice and stable, you should see something that looks fairly similar to these images here, but here's what you get. Okay, so the original image is recovered very well, but as soon as you start adding a little bit of noise, you get significant artifacts in your recovery. And this is, of course, indicative of the instability of the learned deep neural network. So I want to remark here that this is not due to a lack of training data. It is true that in a lot of imaging problems, especially medical imaging, your training data is quite limited. But even if you had a lot more training data, you would still arguably still see these effects, okay? Because it is because of the mechanisms that I've described earlier in the talk. Okay, if you're just training, you make yourself susceptible to detail transfer or over and inconsistent performance. So okay, so that's essentially what I said. So your map fails if it recovers details that are close to the null space. You can easily train a deep neural network to inadvertently do this, especially if you just have training data. And yes, you can also not have in general confidence estimates. So I think the takeaway from all of this is that, for safe and reliable imaging, we need certifiable conditions that guarantee robust recovery via deep learning based methods. And so what I want to do for the last 15 minutes of the talk is to talk about some recent theory that we've been working on for posterior sampling with generative models. So this is a relatively recent deep learning based technique for inverse problems. It's become increasingly popular. It's a Bayesian technique, and so I'm gonna talk about some recovery guarantees for this problem. So okay, so in order to do that, I first need to have sort of one slide on generative models. So let's suppose we have some unknown probability distribution on Rm. So this is distribution of images. So think of this, for instance, as a distribution of brain images. Okay, so if I draw things from my distribution with high probability, I get something that looks like a brain. With low probability, I get something that looks like a donkey, or something that looks like this, or something that looks like the ChatGPT logo. Okay. Now, suppose I have training data. So I have images drawn IID from my unknown distribution. And what do I do in generative modeling? So first of all, I start with a latent space. And this is typically something like R, and I think this should be K. So RK. And I put a distribution on my latent space. Normally, this is a very simple distribution, so let's just think of the standard normal distribution. And the idea of generative models is to use my training data to learn a deep neural network, G, that maps from my latent space to my image space, so that the push forward distribution, so when I push forward gamma through my deep neural network G, I get something that's close in some suitable metric on probability measures to my unknown distribution R. So, okay, so that's my one slide on generative models. I'm not going to talk about different architectures, GANs, diffusion models, et cetera, et cetera. I'm not going to talk about how one does this in practice. We're going to assume, in a sense, that someone has trained a generative model for us. Okay. So let's say off the shelf, we're able to pick a trained generative model that's been trained to produce, say, brain images. So what is posterior sampling of generative models? Okay. So posterior sampling of generative models is very straightforward. We take our generative model, we can now use that to define an approximate prior. And then we're going to recover by sampling from the posterior. Okay. So given measurements y equals ax plus e, we're going to think of our recovery x hat as a sample drawn from the posterior distribution, p given y, also comma a if a is random as well. So this is, as I said, this is increasingly popular. It has some benefits. First of all, it's unsupervised because the generative model is just trained on images. You don't need the measurement data. You can also use off-the-shelf models. So as I was just saying, the training process is really separate from the image recovery process in that sense that you just train your generative model off the shelf. And then when you want to go and solve inverse problems, you just pick that off-the-shelf model. Also, because it's inherently Bayesian, you can use it to compute uncertainty estimates as well. Of course, there are downsides as well. Sampling from the posterior is often expensive. That's perhaps the key downside. However, I would say with score-based diffusion models, there are sort of emerging techniques to do this fairly efficiently. The idea being that to sample from the posterior, you need to just adjust the score functions using your given measurements, and then you can run your diffusion process using those adjusted score functions. Okay, so we'd like to try and provide some recovery guarantees for posterior sampling with generative models. So here's a setup we're going to think about. We've got our real image distribution R. We've got our learned image distribution P. So think of P being close to R. Now we're going to assume that we have a distribution A for our measurement matrices. Okay, so this is a distribution on the space of n by n matrices. And we have a noise distribution as well. We're just going to assume our noise is just standard Gaussian noise for convenience. Our framework will handle other types of noise, but let's just assume it's Gaussian noise. Okay. So I'm a sort of, I come from compressed sensing. I did a lot of work on compressed sensing back in the day. So whenever I try and look at a problem like this, I try and think of it sort of by analogy with ideas from compressed sensing. Okay. So what do you have in compressed sensing? In compressed sensing, you have a low complexity model class. Okay. So for instance, the set of sparse vectors, where the complexity of the model class is measured by the sparsity. So now we're talking about distribution. So we're going to think about a low complexity distribution in some sense. And we'll make this concrete in a second. Okay. So that's the first sort of component of compressed sensing. And then what's the second component in compressed sensing is you need some kind of condition. So for instance, a restricted isometry property on your model class, or more precisely on the difference set of your model class. Okay. Well, now we have a distribution. So what we're going to replace this with is some kind of concentration behavior on the difference set of the support of the distribution. Okay. So I'm trying to draw an analogy here with compressed sensing, which might help people who are sort of familiar with that. I do want to caution, though, that despite this analogy, which is kind of useful for understanding what's going on, the proof techniques that you use for the theorems I'm about to present are really completely different to the sort of standard compressed sensing proof techniques. Okay, so let's talk about the complexity of a distribution. So the first key question you have to answer is, okay, what's a suitable way to measure the complexity of a distribution? And fortunately, we were able to build this work on some prior work of Jalal and co-authors. And one of the things that they introduced was this idea of an approximate covering number of a distribution. Okay. So given delta and eta greater than or equal to zero and a distribution P, I'm going to define the approximate covering number as the minimum number of balls of radius eta that I need to cover at least 1 minus delta of my distribution. So here's the picture here. Here's just a nice standard normal distribution. I could take my balls just to be just equal size intervals of half width eta, and then I just figure out how many of these I need so that the total area under the curve is at least 1 minus delta. Okay, so why is this a reasonable thing to think about? Well, one argument that you can give is that generative models have low complexity in this sense. Okay. So here's a proposition. It's a fairly straightforward exercise to establish, and it says the following: suppose I have a Lipschitz continuous map with Lipschitz constant L, and I look at the push-forward distribution, where my distribution on my latent space is just the standard normal distribution. Then the log of the approximate covering number is bounded by k times a log factor. So this is kind of what you want. Okay, it's saying that the log of your covering number is log linear in the dimension of your latent space. So this is very much suitable if you have a generative model like a GAN, where the latent space dimension is relatively small in comparison to the image dimension. This is saying that your complexity of your distribution is really measured by the latent space dimension. Again, it's also logarithmic in the Lipschitz constant, so you could have quite a large Lipschitz constant and not have problems. And again, you're logarithmic in eta and double logarithmic in delta. Okay. The interesting thing about this result as well is actually all it uses is Lipschitz continuity. So it doesn't actually require you to be looking at a deep neural network. So in that sense, it's rather powerful. If you have any kind of push forward measure from a small latent space, then you have low complexity. Okay, so with that in hand, let me present our sort of abstract result. Okay. So I'm just gonna make one assumption for convenience. This can be removed, but it gets a little bit more messy in terms of the theorem. For convenience, I'm going to assume that my distribution of my measurement matrices produces measurement matrices that are almost surely bounded by some number theta, okay, which you can just take equal to 1. Okay, so suppose that I have P between 1 and infinity, delta epsilon and eta bigger than 0, and I have this lower bound on sigma, which is the standard deviation of my noise. Then, for any d, we'll talk about d in a second, I get stable and accurate recovery with high probability. So the probability that x star, which is my ground truth image, minus x hat, which is my sample from my posterior, is bigger than essentially d squared times by eta plus sigma. This is small, this is less than delta, provided two things hold. So first of all, my ground truth distribution and my learned distribution are within epsilon, epsilon divided by 2m theta. So keep in mind here, I should have said this more clearly, x star is being sampled from R. So it's being sampled from my true distribution. X hat is being recovered from my approximate posterior, which is based on P. So I need closeness of my distributions. And then the second condition is I need essentially concentration. So I have my covering number here, and then I have this factor in brackets here. Ignore the exponentially small term that comes from the noise, but let's focus on these two terms here. So these are what we call lower and upper concentration factors. Okay, so if I take for instance, the upper concentration factor, this is measuring the probability on draws of my measurement matrix that the 2 norm of AX is greater or equal to D times by the 2 norm of X. And then I take the supremum over all X's that live in the different set of my support. Okay, so you can think of this as kind of similar to some kind of RAP type condition. Okay, so this is the abstract result. It's a little bit unclear kind of what this actually means for situations that we're interested about. But what we can do is we can take this abstract result and look at particular types of distributions and measurement matrices that we might be interested in and derive some concrete bounds on the number of measurements that we need. So an example that I always like to work with is the example of Fourier imaging or Fourier sampling. Yeah. So what is Fourier sampling? This means that your measurement matrix A is of the form PF, where F is your discrete Fourier matrix, so n by n, and P is a row selector matrix. Okay, so it's a matrix of zeros and one, an n by n matrix of zeros and one with one non-zero per row, and the location of the non-zero is essentially telling you which frequency you're going to sample. Okay. So Fourier sampling is a sort of very important type of sampling for imaging. It's a sort of straightforward model for MRI. It also rises in NMR, radio interferometry, helium atom scattering, lots of other applications. So it's a very important case to be able to try and understand theoretically. Okay, so we're going to make things fairly simple. Um, we need to think about some kind of random sampling. So we're going to think about just the simplest random sampling for the moment. So we'll look at the distribution of images where where the rows of P are just chosen randomly and uniformly. So in other words, we're randomly sampling frequencies in Fourier space. Okay, so then we need one more component. So again, I sort of put my compressed sensing hat on here and think because we're randomly sampling in Fourier space, we don't want our distribution to produce images with highly localized Fourier transforms. So how do we measure this? We can measure this by defining what's called in compressed sensing often a coherence. Okay, so coherence is measuring exactly this localization property. It's telling you essentially for something in the difference set of the support of your distributions, how large is its Fourier transform at a point divided by the Fourier transform of the image in the two norm. Okay, so with that in mind, we can specialize our result to say something about Fourier sampling. So here we have the same statement on stable and accurate recovery. Again, provided we have closeness of our distributions, but now we have this fairly explicit looking measurement condition. The number of measurements we need is linear in the coherence times by the log of the covering number plus a log term in 1 over delta. Okay. So we have stable and accurate and therefore in particular hallucination-free recovery, provided we're linear in our model complexity and linear in the coherence. Okay. And as we've seen, we can estimate the model complexity theoretically. We know that it scales log linearly in the dimension of the latent space. And also for generative models, you can estimate this coherence empirically in a lot of cases, and in some cases theoretically as well. So these are, in some sense, sort of conditions that you can check in practice to test whether you have enough measurements. Okay, so just one final slide before I wrap up. There are many situations where your coherence might be high. And in this case, if the coherence is high, this might say that you need many, many measurements to do recovery. But what you can do is, again, you can take ideas that were sort of first formulated in compressed sensing and generalize them to this setting as well. So you can change your sampling distribution. So rather than sampling purely randomly in Fourier space, you can do some kind of local coherence sampling. So essentially, you define a local coherence, which is saying how large is the Fourier transform at a given frequency for something in the support of my distribution. Use that to define a probability distribution on k-space, and then sample randomly according to that distribution. Okay? And this works very, very nicely. Okay, so especially when you have a small number of measurements, this gives you a significant boost in the recovery quality. It also gives you a significant boost in the variance of the error as well. Okay, so you get significantly smaller variance too. Okay, so let me wrap up there. So to summarize, deep learning methods have shown great promise in inverse problems in imaging, but they're prone to hallucinations. Uh, we talked a lot about hallucinations. I guess the takeaway is that there's a pressing need for theoretical guarantees that guarantee stable and accurate, and therefore hallucination-free recovery. I introduced a theoretical framework for stable and accurate recovery when using posterior sampling. Um, and let me stress that although this was motivated by generative priors, the framework itself is actually very general. So it actually provides novel, non-asymptotic guarantees for Bayesian inverse problems in the setting of discrete linear inverse problems. So we're working on this a lot right now. Myself and my student Nick, we're working on extensions to infinite dimensional inverse problems, nonlinear problems, also looking more at diffusion models as well, trying to understand their complexity and various other things as well. So in there, just to mention a few references. So this is the paper that I talked about on hallucinations. This is the recent paper on posterior sampling, which appeared in Europe's last year. These are a couple of other related works as well that talk about sampling in more detail. And finally, I'll just give a brief plug for my book. If you're interested in imaging, especially model-based imaging methods and a little bit of deep learning as well. So I have a book with Anders Hansen titled Compressive Imaging. Okay, so I'm there, and thank you for your attention.
All right, let's smash those reaction buttons.